Hello, we are online now. Good afternoon, good morning, or good evening, depending on the place of the earth you are located now. I am Eduardo Freitas. On behalf of the Galileo Information Center in Brazil, I welcome everyone to this online workshop on global navigation satellite systems, signal processing, and navigation techniques. Galileo Information Center in Brazil has the objective of dissemination and promotion of Galileo satellite information and to promote new applications. Thanks for your attendance. And now I would like to introduce Mr. Felix Antreich, Adrià Rovira Garcia, and Jaume Sanz, the presenters, the speakers in this webinar. And now you can start your presentation and introduce yourself.
Hi, my name is Felix Antreich. I'm a professor at the Aeronautics Institute of Technology, ITA, in São José dos Campos. And I will start with the first part of the webinar.
Good afternoon. I am Adrià Rovira. I am a lecturer at the Universitat Politècnica de Catalunya, and I will continue the webinar with the second part on overview of the GNSS navigation techniques.
Hi, everybody. My name is Jaume Sanz. I'm professor in the Universitat Politècnica of Catalonia in Spain, in Barcelona, and I will give the last part of this seminar.
Okay, I will start sharing my screen and I will start with the first part.
Okay, Felix, when you share your screen, I can give you your, okay, so everything is okay. Okay, we are seeing now your screen in the presentation mode. Thank you.
Great. Okay, so welcome to this webinar. I will start with the first part, which is an overview on GNSS signals and basic signal processing. We will start with getting to know about multiple access schemes. So several satellites need to share the same transmission medium and broadcast to the GNSS users to enable positioning. The satellites need to share the transmission medium such that the GNSS users can separate the different satellites, perform ranging, and receive the navigation data from each of the satellites. This is very important for positioning, and this is the purpose of the signal. The satellites need to share the available bandwidth by using channel access or so-called multiple access MA techniques. MA techniques have the aim to ensure that the signals of the different satellites will be separated and even orthogonal. In general, there are three basic MA techniques: time division multiple access, TDMA, frequency division multiple access, FDMA, or code division multiple access, CDMA. Here you can see three graphs that show the functionality of these three MA techniques. For time division multiple access, the different users, or in our case, the satellites, transmit in different time slots, and they use the complete available bandwidth to transmit. In case of frequency division multiple access, the satellites use only a part of the bandwidth, a subband, and they transmit all the time all together. In case of code division multiple access, the different satellites are separated by using different codes, and they're transmitting all together all the time, and they're using all the complete available bandwidth. In principle, each of these techniques can achieve the same aggregate spectral efficiency. So this means they achieve the same symbol rate per user. In our case, this is a satellite. Number of users per channel, so satellites per channel, and the sum symbol rate of all the satellites. These basic MA techniques can also be combined to form hybrid combinations. So for example, frequency division, time division, FD, TDMA. or frequency division and code division, FD-CDMA, and many others. For GNSS, we have to consider that the number of in-view satellites, so that broadcast to users, is quite low, so around maximum 12 per system at the same time. Data transmission demands in general do not play a prominent role in GNSS. And mainly other performance measures have to be considered when choosing the appropriate MA technique. Signal design properties for GNSS are synchronization accuracy, which means the capability of estimating time delay, Doppler, and carrier phase in order to calculate pseudorange and then position. The robustness of this synchronization and time and parameter estimation. Inter-system multiple access, MIR, or spectral separation, so interference between different GNSS. Intra-system multiple access interference, MIA, so the intra-system interference between different satellites of one system. Interference robustness with respect to other systems that share the same bands, for example, radar systems, multipath performance, and others. Most GNSS, GPS, Galileo, and Beidou use direct sequence CDMA, DS-CDMA. In this case, each satellite uses a different code or spreading sequence for transmitting its signal. Spectral separation between different GNSS and their services in the same frequency band can be achieved by using different modulation schemes. And thus, all these systems achieve an FD-CDMA, so frequency division, code division, multiple access. The only system that uses a different approach is GLONASS, the Russian system. They use a CD-FDMA approach. Here, each satellite transmits in a different subband using the same spreading sequence. Here you can see the power spectral density of different GNSS signals of GPS and the Galileo system. And you can see how they are spectrally separated due to their usage of different modulation types. For example, we have the GPS course acquisition signal in black. This is the signal that you use all in your phones today to navigate. Then we have in blue the new open service of GPS, the L1C signal, and the open service of the Galileo system. This you also may already use in your phone if you have a newer model. And then we have in green the new GPS military service, which is called M-Code, and the public regulated service of Galileo in red. So let's understand what are spread spectrum signals. The received direct sequence code division multiple access or code division frequency division multiple access baseband signal of one satellite can be given by X of t, while P is the signal power, C of t is the pseudo-random spreading sequence or the code that the satellite uses, tau is the time delay or propagation time delay, G of t is the binary navigation data message, and N of t is white Gaussian noise with power spectral density of N0 half. The PR sequence, spreading sequence, can also be given by this formula, where here this is the Kronecker function, and this is the convolution operator. P of t is the chip pulse shape, which is not necessarily restricted to be time limited to only one chip interval. TC is the chip duration. The PR sequence is given by its bits, denoted by DM. TD is the duration of the sequence. and ND is the number of chips of the PR sequence. The autocorrelation function of the spreading sequence can be given by this equation. And if we apply Parseval's theorem, we can reformulate this equation, and we end up with a formulation where we have here the power spectral density of the chip pulse shape given by the Fourier transform of the chip pulse shape, and then we take the absolute square of that. And we have here the power spectral density of the sequence. If the sequence is not only pseudo-random but random, then we end up with this formulation, where the autocorrelation function of the code or the spreading sequence is only dependent on the power spectral density of the chip pulse shape. And we have assumed here that the chip pulse shape is normalized to 1. Yeah, P of F is the Fourier transform of the chip pulse shape. The sequence is assumed not only pseudo-random but random, and then the power spectral density is equal to 1. This will be important for the time delay estimation, which we will discuss later in this part. The receiver performs correlation with a period T of D using a replica signal based on a model. Usually this model is based on the signal in space interference, or interface control document, which is available for all the systems. And with this, the receiver creates a replica signal in order to correlate the received signal with this. So in case the time delay tau is known to the receiver, we can now write correlation. Here is the received signal of the desired satellite that we want to receive. We correlate with this model code that we have generated in the receiver. We also have received noise, so the noise will also be correlated with this replica signal. We end up with the navigation bits at the instant k and a noise term, while k runs from 0 to k minus 1, and the navigation bits are binary. The power of the signal and the noise after despreading, so after correlation, can be given as. So we can calculate the expectation of the correlation result, and we arrive with the power. And we can also calculate the expectation absolute square of the noise term, and we arrive with the noise power, which is n0 over 2 td. With this, we can calculate the signal-to-noise ratio after despreading or correlation. So now consider that the reception, or that we not only receive one satellite, but we receive n satellites for either a DS-CDMA or CD-FDMA system. Again, we are correlating with our replica signal for the desired satellite signal, which is here. And then we correlate with all the other I1 to NSAT minus 1 satellites that we also receive in the same band, but they're using different codes. And the correlation between C and any CI usually is very, very small. The codes are designed to minimize this interference, which is here now the intra-system multiple access interference. And this term can be considered quite small, so approximately 0. And also the noise again. And so at the output of correlation for this, with this replica signal C of t, we arrive with the signal of, or the navigation message of the desired satellite plus a noise plus, and additionally plus multiple access interference. In case of direct sequence CDMA, the satellites are separated using different PR sequences, while in case of CD-FDMA, the signals are separated spectrally in different subbands, and all signals use the same PR sequence. This is the case for GLONASS. Yeah, the receiver usually works with digital signals. So the observations are collected, or the signal is collected, is sampled at n time instances in k periods. Thus, we can arrive at a digital signal x of k capital N plus n, and this is equivalent to the samples of the continuous signal x of t, where n is running from 0 to n minus 1, and k is running from 0 to k minus 1. And ts is the so-called sampling duration, which is here equivalent to 1 over twice the receiver bandwidth equals b. A simplified model of the received baseband signal after sampling can be given as. So this is a very simplified model, but this is very useful for what I want to show you in the following slides. We have here the antenna that is receiving our signal with all the amplifiers, and the antenna and also the amplifiers, they introduce additive Gaussian noise. Then we have here the receive filtering, which is modeled by a low-pass filter of bandwidth B. Here, this is the Fourier transform of the low-pass filter HL of t. And after this low-pass filtering, we perform sampling and digitalization of the signal, and we arrive with this digital signal. So thus, with the duration now of the sequence is equivalent to the number of samples that we took times the duration, the sampling duration Ts, and this is equivalent to n over 2b. And we can now derive a vector formulation of our signal. So we have the signal vector x of period k. We have the vector c of k parameterized by tau, so of our spreading sequence, and we have a noise vector. All these vectors have n rows and are column vectors. And all these vectors can be defined now by these equations, where this means transpose here, and you can see that the signal vector x includes all the signal samples, the noise vector includes all the noise samples, and the vector c includes the delayed spreading sequence, also sampled at nts. And this is always for one period. So now, how does the receiver perform time delay estimation? So for x, if we consider only the first period, so x of 0, and we call this now x, let us assume a random variable x that has a multivariate Gaussian probability density function PDF parameterized by the parameter tau, and thus we get this this equation. This is a normal distribution, and this is the probability density function of the random variable x. The likelihood function with respect to the parameter tau is given as, so the likelihood is equivalent to the PDF. The likelihood is a function of the parameter tau, which is to be estimated at a given realization of the random vector x. And the realization in our case is our received signal. So we are receiving a realization of a random variable, and then we're trying to find the parameter tau that parameterizes this received realization. On the other hand, the PDF is a function of the realization of the random variable for a fixed value of the parameter tau. So these are two separate definitions, but they are equivalent. It's only different in the way of looking at it. We will now consider the likelihood function, and we're using the likelihood function to find an estimate for tau, which is called a maximum likelihood estimator. So we take the likelihood, and we receive a representation of our random variable x, so our signal x at one period. And we're trying to find now a time delay that is maximizing the likelihood with respect to this received signal x. We can also, and this is maximization of this argument. So we can also, instead of maximizing the likelihood with respect to tau, we can also maximize the log likelihood with respect to tau, because the logarithm is a monotonic function. So the MLE is asymptotically, so the maximum likelihood estimator is asymptotically large, asymptotically unbiased and efficient for large n. When further deriving the estimator, we can now write, taking the normal distribution that I showed you on the previous slide, and we get these three terms. This term is not, the first term here is not dependent on tau, so we can neglect this, and we can also get rid of this term here, or neglect this term, because it's also not dependent on tau. We're trying to maximize the function only with respect to tau. So now let's concentrate only on the third term here, while this is the L2 norm of the vector. So let's concentrate only on this part, and we have expanded this part into another, again, into three parts. While this part, again, is not dependent on tau, we can therefore neglect this in the maximization, and this part is constant. Because for any kind of time delay, the L2 norm of this vector is constant, is approximately n, capital N. So now we can only focus on this part in order to find the maximum of tau. So as the first term, as I said already, does not depend on tau, and the third term is constant with approximately the L2 norm of the vector c of tau equal approximately n. And we can also drop these two factors here in front of the second term, so 2 and the square root of p. We end up with this maximization. And if you remember what we talked about correlation, this is correlation in discrete. We wrote the correlation in a continuous form earlier in this part, and this is the correlation in discrete. So we have the signal that is multiplied. We take the transpose of the signal vector and multiply this with our replica signal for a given tau. And we do this for many taus, and we're trying to find then the maximum of this function j of tau. And this is then our estimate tau hat, so of the time delay. In practice, time delay estimation is performed using a delay lock loop, a DLL, applying what's called a gradient ascent method with a step size of mu larger than 0, where the kth iteration can be given as, so for the kth period also. So the estimate of the time delay tau hat of k is then given by the previous, the estimate of the previous time instant, tau hat k minus 1, plus the derivative of this cost function that we had just derived, which is the cross correlation between the received signal and our replica, multiplied by the step size. The derivative here in this formula here can be approximated using the central difference quotient of length 2 delta. And we can introduce that here in this formula, where we can see we have now here the we have a delayed signal by plus delta and delayed by minus delta, the cost function. And we evaluate two values of this cost function, and for this and divide it by 2 delta, and with this we can approximate the derivative of this this derivative here of the cost function. And we can plug in now from the maximum likelihood estimator the cost function, which is the cross correlation. Or if the signal is matched to our replica signal, so the transmitted signal is exactly the same, has exactly the same characteristics as our replica, this is even equivalent to the autocorrelation function. A stochastic version, considering successive periods k, can be given as. So we are now introducing successively new observations, so new periods of the signal, and we're performing correlation with plus delta and with minus delta. This usually is called early correlation, because this is cross correlation with 2 delta, advanced a little bit, and this is the what's called late correlation. So correlation and then c the vector c delayed by delta, and that's why the DLL then is called an early minus late delay lock loop. Yeah, without noise and assuming that the receiver uses signal match correlators, the discriminator S-curve for a coherent early late DLL can be given as. So this is what we just discussed before, which is determine our steps, is called S-curve in the delay lock loop. And we can also write this with dependent on K. This illustrates how the delay lock loop now is finding the peak of the autocorrelation function or cross correlation function, and with the gradient ascot method. So we start here, for example, we have the time instant k minus 1. We calculate here the early correlation and the late correlation. These are these two values. And then the DLL will drive us in the next step to the peak of, closer to the peak, and finally to the peak of this autocorrelation or cross-correlation function, where then early needs to be left of the peak and the late correlation needs to be right of the peak. And with this mechanism, the delay lock loop is tracking the signal over time. Signal processing steps in a GNSS receiver. There are three main steps. So acquisition, tracking, and navigation processing. Initializing the tracking is performed by a process that's called acquisition, signal acquisition. This process also finds out what kind of satellites are available and can be received by the receiver, and then the tracking with the DLL and also with other parameter tracking methods for carrier phase and Doppler shift are initialized, and all the satellites are tracked continuously until we lose log for that. So we lose the tracking of this of the signal, and then we have to restart, have to go back to the acquisition again and initialize tracking again. The tracking provides certain estimates to the navigation processing. Usually this is time delay, Doppler shift, and carrier phase, and based on these estimates, what's called a pseudorange is calculated, and with pseudoranges, navigation and positioning can be performed. So we have seen how time delay estimation works. We have seen that time delay estimation is dependent on the chip pulse shape and the autocorrelation function of the signal. And we have also seen how the different satellites are separated by a multiple axis scheme. So now let's, in the final couple of slides, let's review some of the basic chip pulse shapes that are used today. Let's start with the rectangular chip pulse shape. The rectangular chip pulse shape can be described by this equation, where u of t denotes the unit step or Heaviside unit step function, u of t. So everything above 0 is 1, and everything below the time 0 is 0 in this function. And we also assume that the chip pulse shape, the rectangular chip pulse shape, is normalized. The rectangular chip pulse shape can be considered as the classical chip pulse shape for direct sequence CDMA systems. If you open any kind of book on this, you will find rectangular chips described. Also, for many signals of GNSS, for example, in the GPSCA code, the L5 signals of GPS, the E5A and E5B signals of Galileo, and many signals of Beidou use rectangular chip pulse shapes. And we get a binary phase shift keying signal. Here on the left-hand side, you can see the chip pulse shape, so it's a rectangle. And on the right-hand side, you can see the modulation diagram where we have the real part of the received signal and the imaginary part of the received signal, and we have only two states, so it's a binary phase shifted, binary phase shift keying signal. On the left-hand side here, you can see the autocorrelation function of this signal. So it's a triangle, a perfect triangle for infinite receiver bandwidth. If we have a real system with a limited bandwidth, this gets a little bit rounded. But in principle, it stays very close to a triangle. And on the right-hand side, you have the power spectral density of this signal, which is kind of a sinc function with one lobe that is located around the carrier frequency. Here we can also see that on the left-hand side in the autocorrelation function, we have a very sharp peak, and this peak usually determines how exact can we synchronize with the received signal and how exact can we estimate the time delay. Another set or another kind of signals that are used by many GNSS are binary offset carrier signals, box signals. And they became kind of the standard of GNSS signal design besides using rectangular chip pulse shapes. Their chip pulse shapes are formed by the product of a rectangular pulse. This is the rectangular pulse here, and a sine or cosine square wave subcarrier, which can be given by this function g of ns of t, where nc is the chip rate, ns is the subcarrier rate, fr is the reference frequency. This is usually 1.023 megahertz. And then what's called a Bock NSNC signal is a sine subcarrier signal. And then there is the Bock cos NSNC is a cosine subcarrier signal, Bock signal. The Bock signal pulse shape can be given by this. So it's the multiplication of this rectangular pulse with the subcarrier wave. A Bock 1-1 sine wave subcarrier is also known as the biphase Manchester pulse. And we also get a BPSK, so a binary phase shift keying signal again. Bock signals achieve the frequency division, code division, multiple access that we have seen earlier in this presentation. And you will see in the following slides how they do this. So this is the chip pulse shapes for a cosine on the right-hand side, and on the left-hand side, a sine Bock 1-1 signal. Here's the autocorrelation function of the Bock 1-1 and Bock cosine 1-1 signal. We can see here that the Bock cosine signal or chip pulse shape has a sharper peak, which indicates that with this signal we have a better performance in estimating the time delay. However, these chip pulse shapes have quite high side lobes here and also here, and they can interfere with our synchronization process, because as you have seen earlier, the receiver tries iteratively to track, he is initialized somewhere here in this area of this autocorrelation function, and then tries to find the peak and tries to track the peak. However, if we initialize farther out here, or if there's a lot of noise, the delay lock loop can slip out here, and we can maybe even stuck in a side peak. And this is what I mentioned earlier with synchronization robustness. Yeah, the power spectral density of the two chip pulse shapes of the Bock 1-1 and the Bock cosine 1-1 are given on this slide. And we can see it's a split spectrum. So we have no power at the carrier. And the Bock cosine has a little bit more power shifted towards to higher frequencies. Just for an example, we can also have a look at Bock 4-1 or Bock cosine 4-1 chip pulse shapes. On the left, you have the Bock sinus 4-1, and on the right-hand side, you have the Bock cosinus 4-1 chip pulse shape. We can also check out the autocorrelation function. Here we can see that we have very high side lobes, but also a very sharp main peak here for both of these chip pulse shapes. And finally, we can have a look at the power spectral density of these two chip pulse shapes. And here now we can clearly see how we can realize the FD-CDMA. So we can spectrally separate different signals inside the same band using Bock chip pulse shapes or binary offset carrier modulation. And we can also see that the Bock cosine signal has more power shifted to higher frequencies and less power shifted to lower frequencies. And the Bock sinus chip pulse shapes has more power shifted to lower frequencies and less power shifted to higher frequencies. So then, thank you very much for your attention, and I will hand over now to my colleague Adrien. He will continue with navigation and positioning techniques.
Thanks, Felix, for this very nice overview on the signals. Now I will share my screen. So welcome to the second part of the lecture today. We will talk about the different positioning techniques. And the first part will be done by myself, and then the next part will be done by Jaume. This is the layout of the presentation. So we will introduce the GNSS positioning concept. We will talk about the easiest and most common positioning, that is the standalone, and then we will talk about the differential positioning, which we distinguish the code-based differential positioning and the carrier-based differential positioning. And the lecture will finish reviewing some of the commercial services that are available today. Okay, so let's start presenting the positioning concept. This is the standalone positioning, where by standalone we mean that the receiver is performing a positioning completely autonomous. So it only uses information that is broadcast by the orbit, by the satellite. We have an illustration of what we mean. Here we have 4 satellites that are broadcasting measurements, orbits, and clocks, and the user, the receiver, is computing the position. This is what we can achieve in any handheld device, like a smartphone, a car navigator, and so on. But the second type of positioning that we will talk today is differential positioning, in which we are augmenting the data that we are receiving from the satellites. And this can be done using different strategies, as we will see. To clarify, here we have a picture of 2 receivers. We have a receiver that is on board a mobile tractor that is moving, and then we have a reference station nearby in which are sending the measurements, and then we can perform this differential positioning. The idea is that we need more than one receiver. Of course, we can have multiple receivers. We can have a network of receivers distributed to cover one continent. As we will see during the lecture, we can have a very good accuracy that we will see. So let's now introduce this standalone positioning. In the standalone positioning, we are receiving the measurements that we will talk about, and we use the information broadcast by the satellites. And what is the typical accuracies that we can achieve using the standalone positioning? If we look at the error, and by error we mean the difference of the coordinates estimated with the standalone with respect to true, we can see here in the top right of the slide that we can achieve errors of few meters. And we have different components. We have the north error component, the east error component, and the up error component, but you can see that they are on the range of few meters. If we look only at the horizontal plane, and this is what we have in the bottom right plot, and we can see how the dispersion of the points around the 0, 0, the truth. And this, we need to talk about the errors on the signal. We have seen this dispersion of the points. The points are not all of them in 0. And we will talk now what are the reasons that explain these errors. Well, this slide illustrates what are we measuring. We are measuring a distance from the antenna of the satellite to the antenna of the receiver. We are measuring the traveling time of the radio signals that are broadcast by the satellites. And this is done, we have two types of measurements. We have the code measurements and we have the carrier measurements, that we will see how different they are. In this traveling time, there are many effects that we have to take into account. We have to correct these measurements that are affected by several errors. We can see in the left plot, we can see that together with the geometric range, that is what we are interested into measuring, we have all sources of errors. We have errors at the satellite, we have errors, relativistic errors, we have instrumental delays, and so on. We will see all of them and how we can remove them. Regarding these two types of measurements, it is important to take account that they are very different. We have in blue depicted the noise of the code measurements. The code measurements are noisy, as you can see in the plot, but are unambiguous. They are an absolute measurement. In contrast, and this is what we have in red in the plot, we have the carrier. The carrier measurements are very, very precise. You can see zoom illustrating the noise of these carrier measurements that are at the millimeters. But from time to time, we have discontinuities. We have discontinuities in the carrier phase tracking. This is what we called the cycle slips. And then we have to be careful, and there are techniques to detect these cycle slips. This figure illustrates the different noises that can be expected in the code and the carrier. We have in green, we have the code measurement, and we can see that is noisy. They present typically a butterfly effect. And we have the carrier measurements in blue. And then we can see that they have the same shape, and the two plots, the two are parallel, the code and the carrier phase, but the noise is very, very different. But we have means to take the carrier to align the carrier to the code measurements. And this is what is illustrated in this plot. This is the well-known Hatch filter that is aligning in real time by computing the difference between the code and the carrier. Here we have the formulation that is very easy, it's straightforward to have this carrier smoothed code that we will see that we can use to improve the positioning. Respecting the errors that are affecting the carrier phase measurements, we have many of them. This slide illustrates some of the most common errors that we have to deal in GNSS positioning. We have errors in the satellite clocks. We have also errors in the relativistic effects. We have to be careful that to compute the satellite coordinates at the mission time, because the satellites are moving at few kilometers per second, and then the signal takes some time between the emission and the reception, and we have to take into account that the satellite is moving. Then we have the ionospheric delay that is very variable. It has a strong dependency with the time, with the geographical location, and the solar cycle, and so on. We have the tropospheric effect, the tropospheric delay, that is the lower layer of the atmosphere, and then we have biases. And we can see, and all of these plots illustrate the effect of taking into account or not taking into account these model terms in the user positioning. And we can see that the impact in the coordinates that are being estimated using or not using these models are very, very important. Okay, so now that we have introduced this standalone positioning and some of the errors that are affecting the signal, let's talk about the differential positioning. The differential positioning, we have already seen this slide, but now let's analyze this idea, the idea in which the errors that we have seen in the previous slides that are affecting GNSS, no matter if it's a standalone or differential, those errors are always present. The key idea of differential positioning is that these errors are similar for users that are separated some distance, tens, hundreds of kilometers. So all of these errors, some of these errors that we have seen, we can mitigate, we can eliminate when using more than one receiver. And this is the key idea behind the differential positioning. And we will see how in the remaining of the session, different techniques that exploit this very simple, this very attractive idea of the differential error mitigation. In order to clarify, and in order to categorize the errors that we have seen in the signal, it is typically distinguished by the segment. We have errors that are generated in the space segment, and this basically corresponds to the errors in the clocks, in the satellite clocks, or errors in the orbits, errors that are in the satellite positions, the ephemerides errors. Then we have the propagation errors that are basically, we distinguish between the upper layer of the atmosphere, the ionosphere, and the lower layer of the atmosphere, that is the troposphere. And then we have local errors that are basically at the receiver or the antenna of the user, that are more on the, depending on the surroundings or the particular environment. And we can see how these errors, how correlated are those errors. We have the clock errors that they are common errors, so they can be completely cancelled in differential positioning. We can see that there are the ephemerides and ionospheric errors. They show a strong spatial correlation. So we will eliminate quite a lot of these errors that are shown in red. And then we have the troposphere. The troposphere is a very local delay. This is why it shows a weak spatial correlation. And then the last category are these errors that are very, very local, and they do not show any spatial correlation. They are basically independent. The antenna of the reference site is completely different, can be completely different with the antenna or the environment of this moving receiver. Okay, so now let's see an example of code-based differential position, and this differential GNSS that is using smoothed codes. Remember the Hatch filter. So this slide illustrates the code-based differential GNSS. Here, the key idea, we have a reference station with known coordinates. We precisely know where is this station. And we have a user. We have a nearby user that is shown in blue. Then the idea is that at the reference station, we are measuring the pseudoranges to a satellite, to a particular satellite. This is what we have here with PREF, the pseudorange measured by the reference station. Because we know where this station is, we can compute the geometric distance. And this is what we call the range. We depict with a rho, so that we can compute the difference, what we call the pseudorange corrections. This is the PRC, the pseudorange corrections. That is the difference between the pseudorange that we are measuring and the range that we are computing. And this takes into account that there are errors. For example, if we take as an example the ephemerides error, for example, we can see that the position that is broadcast by the satellite is in one place, but the satellite is in another coordinate. The actual position is not exactly coincident with the position that is broadcast by the satellite. We can compute this difference, the pseudorange correction, and also we can compute the derivative, what we call the range rate corrections, so that we can broadcast to nearby users what are these two terms, the pseudorange corrections and their variation. And this is what we do in a broadcast message. We are broadcasting these two corrections. So the user, the nearby user, then can correct the measurements, the pseudorange measurements that are collected by the user, can apply these corrections, the pseudorange corrections and the range rate corrections, and then we can remove all of the common errors that are present in the signal in space, the SIS, that are affecting both receivers, the reference and the user. And then we can achieve, and we will see examples of errors of about 1 meter. So in order to show how the code differential GNSS works, we present an experiment that we did in the past, in which we use 3 nearby stations located somewhere in the east coast of the United States. We have 3 permanent stations, so we know where they are. And these stations are 2 that are located in the NASA Goddard Center. This is the Goddard North and the Goddard South, that we assume that is the reference station. And we have another receiver, the USNO 3 receiver, that is located 24 kilometers away from the reference station. And we will see how the differential GNSS works. So if we look at the standalone positioning, for example, the vertical error, and this is what is shown in the top left graph, we can see the standalone positioning. We can immediately notice that the 3 stations, every of these 3 stations is depicted with a different color. They follow basically the same pattern along 24 hours of data. We can clearly see it in the vertical. Also, it's not that clear in the horizontal, but the patterns are common. And this is the idea that we highlighted before, that there are these errors affecting the measurements. They are common. We can see it in the standalone position. So we can take benefit of that in the bottom plots. We can see that by applying these differential corrections, the pseudorange correction and the range rate correction, we can improve a lot the positioning. And in this example, we have now depicted the 2 stations that are navigating with respect to the reference station Goddard South, and we can see in red and in blue, we can see how the accuracy of these stations has improved a lot. Of course, the receivers that are closer, we can see in blue the shorter distance that we call baseline. We can see that the errors are very cancelled, they are very eliminated. On the other hand, we can see that the longer baseline, the baseline of 25 kilometers, it's also working well. but the mitigation is not that high. We can see it both in the vertical, or we can see it also in the horizontal positioning error. We can again see that the shorter baseline has a very good positioning, and then we have the longer baseline that is also mitigating, but not so well. Because, of course, the closer the two receivers are, the more errors that are cancelled. And this is how the information that is being broadcast to the user, how it looks like. We have the PRC, the pseudo-range correction. Remember that is the difference between the geometric range that we compute from the reference station and the pseudo-range measurements. Here we have different satellites that are depicted with different colors. We can see that it's a smooth evolution, and this is because we are using data that is smoothed code. We have applied the Hatch filter, and this data is after May 2000, so that it does not have the select availability activated. In terms of the first derivative, we can see that we can see few centimeters per second, and this enables that we can have some delays in the transmission. So we have the pseudo-range corrections, but thanks to these range rate corrections, how they vary with time, we can admit some delay in the transmission of the corrections. And we can see, just to summarize, we can see the performance of these three permanent receivers in standalone and how they perform. Same data, same receiver, same day, everything is the same, but only by navigating, by using the data in differential mode, we improve a lot the performance. So, in order to summarize what we have seen until now, we have two worlds, we have two approaches so far. Both are using the code. One, and here is depicted on the left-hand side of the slide, is the standalone. What it's generally called standard point positioning, SPP. That is the typical and very common positioning that everyone is used to have on the phone, on the car, and so on. What we can summarize, so the accuracy is a few meters, the coverage is worldwide. We can do it, this standard point positioning everywhere, even in the middle of the ocean, and it's single epoch. We can immediately, after turning on the receiver, we have the final positioning. We will see that in the next positioning techniques, this is not the case. Then, on the right-hand side, we have this differential GNSS positioning that is based on the code. And what we have done, we have improved the accuracy by broadcasting the pseudo-range correction and the range rate correction. And how do we broadcast? Well, we can use many communication channels. We can use internet, we can use telecommunication links, and the way we receive the broadcast message, it's very it can have different ways, different channels. So the performance is that the accuracy that we have by this differential GNSS is that we have a meter level of accuracy. The coverage is regional. This mitigation of the errors is only valid up to 100 kilometers away from the station, but still we are in single epoch. So we can do the differential GNSS immediately. Well, we will see other techniques in the coming slides. And again, and this summarizes this first part of the lecture, is that we are canceling, we are removing common errors, and then we improve the positioning. And now I hand over to Professor Sanz that will explain the carrier-based differential positioning.
Profesor Sanz, creo que no está abierto. Perdón, voy a hablar en inglés. I believe that your microphone is off. Hello? Just a minute, please.
Okay. Okay, sorry for the problem with the microphone. Can you hear me now?
Yes, we can hear you.
Okay. Perfect. Thank you for telling.
Are you sharing your screen?
I'm sharing my screen. Yes.
Actually, I cannot see your screen now. Please stop sharing and do it again so I can tell you if it's okay. Okay.
Okay. Can you?
Okay. Now I can see your screen. Thank you very much.
Okay. Thanks. Thanks a lot. Sorry for these technical problems. Well, welcome to this last part of this webinar. I'm going to present the carrier-based differential positioning, and at the end, some views about the commercial services. In carrier-based differential positioning, okay, sorry, this is not working, sorry. Okay. As my colleague Adria commented before, we have two main measurements to use: code measurements and carrier phase measurements. The previous techniques were based on code measurements or smoothed codes. The techniques that I'm going to present are based on carrier phase measurements, and using carrier phase we can achieve the highest accuracy in the positioning. Carrier phase, you remember this picture, carrier phase is in red, code is in blue. As you can see, code is noisy compared with the carrier phase. Carrier phase is precise, here in red, is about 2 orders of magnitude more precise than code, but the good news is that it's precise, but the bad news is that every time that we lost the signal, when we get the signal again, we have jumps. These are the cycle slips. and the measurement jumps for an arbitrary number, then we have a very precise measurements, but in order to use these measurements for positioning, we have to repair the carrier phase, in general speaking. Let's say we have to estimate what we call the ambiguity. Ambiguity is the jumps in the carrier. Okay, then the techniques that I'm going to present are based on carrier and needs to fix these ambiguities, needs to repair this carrier phase. Basically, we have two main techniques. First is relative positioning. This is the RTK or network RTK, and the second one is the precise or absolute or point positioning, and this is the PPP. This is precise point positioning. Even we have precise point positioning with ambiguity fixing and fast PPP, but these other techniques, PPP with ambiguity resolution and fast PPP, are new techniques that are out of the scope of this presentation, but if you have any question, we can talk about. The first technique is relative positioning. This is the concept of relative positioning. RTK is illustrated in this figure, and in this case we need at least two receivers. We need a reference station and a user receiver, and we estimate the baseline between reference station and user receiver. And the idea is the same as before. The idea is that users in reference station and user in a local area see similar errors, and these errors cancel in differential mode. This means that if we take differences between the measurements of the user and the reference station, the errors due to the orbit, clocks, atmospheric propagation errors, these errors are cancelled or mitigated. Our target is to achieve the highest accurate positioning. This means to achieve centimeter level of positioning, and then everything must be at the centimeter level. This is something that we are going to emphasize in this presentation when working with carrier phase. Well, then relative positioning is illustrated with this figure. We need a reference station and a user receiver, and precise absolute point positioning, PPP, is illustrated in this figure. In this case, what we estimate are the absolute coordinates of the user, and what we use are computed differential corrections from a reference station network, and these computed differential corrections are orbits and clocks. This means the differential corrections are split in these components of the error, orbit and clocks, and the idea is that we obtain the absolute coordinates of the user. In the case of RTK, what we compute is the baseline vector, but if we know the precise coordinates of the reference station, then using this baseline vector, we can compute the user coordinates. Okay. I have some problem with my computer. I have a problem with the computer. Okay. Okay. Okay, we try to disable this. Okay, let's see. Okay. Well, this is a layout of the positioning techniques we are going to present. As Adria commented before, the basic positioning is the positioning that we have in our phone. This is the code-based positioning, the standard point positioning, where we can achieve accuracies at the level of few meters, but worldwide and in a single epoch. Carrier-based differential positioning The highest accuracy is in the relative positioning, where we can achieve centimeter level accuracy in local area and quickly, in few seconds. And in precise point positioning, there is no limitation of the region. In RTK, we have limitation in the region. This is for local area. PPP is worldwide, but it takes longer to converge. We cannot achieve this accuracy in seconds. It can take half an hour and even 1 hour, depending on the satellite geometry. Here we have an idea about these accuracies in standard point positioning using code. The positioning we have in our mobiles, the accuracies at the level of meters. In using RTK, we can achieve centimeter level. This means, in general, we can achieve 1 sigma in the horizontal component, 1 centimeter, 1 sigma, and in the vertical component, 3 centimeters, 1 sigma, which is very, very good positioning. It is quite quick in few seconds. This means 15, 30 seconds, depending on the satellite geometry. We can achieve this highest accuracy, but there is a limitation in the baseline. There is a limitation between the distance between reference station and user. For PPP, we achieve centimeter decimeter level accuracy, but this is what worldwide. There is no limitation in the user location, but it takes longer to converge. Okay, let's go to the first case, RTK, real-time kinematic, the relative positioning. The idea is very simple. What we need is a reference station and user receiver, and the reference station, using a radio link, send the measurements to the user receiver, and the user receiver combine its own measurements with the measurements from the reference station and computes the user solution. In order to compute the user solution, because we are using carrier phase, the user receiver has to repair the carrier, has to estimate the ambiguities together with the receiver coordinate. There is a limitation in the baseline. There is a limitation in the distance between reference station and user receiver, and this is because of the, as we commented before, the concept behind differential positioning is that errors cancel in differential mode. This means reference station, we assume that reference station and user receiver see similar errors, and these errors cancel when we take differences between the measurements. But this is not true when the reference station is far from the user receiver. There is a limitation in the baseline. In the case of code, in the case of using code measurements, the residual error can be larger than when using carrier phase measurements. This is because when using code measurements, the target is to achieve meter level of accuracy, and then residual errors at the meter level are not critical. But in carrier phase, our target is to get centimeter, to achieve centimeter level of accuracy, and then everything must cancel or must be mitigated at this level. One of the main error sources is the ionospheric error, is the differential ionospheric error. And this ionospheric error varies, increments with the baseline, and this is the most limiting factor for the carrier phase differential positioning, in particular for the RTK. Then there is a limitation in the baseline, and this limitation is due mainly to the atmospheric propagation errors. And this limitation in RTK, the baseline is limited depending on the area, the region in the planet, is limited to 10 to 20 kilometers. Baseline, that is the distance between reference station and user. It depends on the region, because in over Europe, we can have baselines up to 20 kilometers, but in Brazil, the baseline is limited to 10 kilometers, and it depends if we have scintillation. If we have scintillation, the situation becomes really, really worse. Well, in these slides, I would like to present two key ideas about how to deal with the ambiguity. As I commented before, the carrier phase is a precise measurement. The noise is at the level of millimeters. Thermal noise in carrier phase is few millimeters. The multipath, if we consider thermal noise and multipath noise is less than 1 centimeter, then it's very precise measurement, and we use these measurements to achieve centimeter level. But we have a problem with the carrier. We have to repair the carrier. We have to fix the ambiguities in the carrier phases. Then how to fix the ambiguities and how to perform this positioning. Here we have two ideas. On one hand, we have to remove errors in the signal. We have to remove differential errors. Errors, as my colleague commented before, as Adria commented before, errors due to the clocks, orbits, atmospheric propagation errors, and so on. Well, taking differences between receivers, we can remove these errors. Even taking single differences, we have a reference station, and we have a receiver, and taking differences between the measurements in receiver, we can cancel this error. In RTK, we are taking not single differences, we're taking double differences. This means differences between pairs of receivers and also pairs of satellites. Double differences between receivers, between pairs of receivers and pairs of satellites. Why? Well, I have to clarify that it is not necessary in order to remove differential errors with single differences is enough. But, well, why not? But in the case of carrier, we use double differences in order to take benefit of the integer nature of the ambiguities. What does it mean? Well, this is the content of the ambiguity term. This is the content of the ambiguity that we have to estimate, the ambiguity we have to fix in order to repair the carrier. And we have a real integer valued part. This is n is an integer number, and we have two additional real valued terms. One term depends on the receiver and the other depends on the satellite. The integer term, n is an integer term, these are integer number of wavelengths. The integer term refers to both satellite and receiver, but these other terms, these real valued terms, one of them refers only to the receiver and the other is the satellite. These are the carrier hardware bias. Taking differences between receivers, we remove what is common for the receivers, that is the satellite. Taking differences between satellite, we remove what is common for the satellites, that is the receiver. And this is the idea of double differences. With a reference receiver, we take differences for the receiver, regarding to the receiver for a given satellite, and taking a reference satellite, we do the same. And in this way, we remove this real valued part, and we have in these double differences, we have the ambiguity term. Double differentiate is an integer number of wavelength. Then we can take benefit of this information in order to fix the ambiguities. And this is the idea. This is the key idea of RTK. How we can proceed? Well, we can start estimating the ambiguity as a real number, like we show in blue, and then we can round up, because we know that this is an integer number in double differences. We can round up this ambiguity, and in this way we can fix, fully fix, we can know exactly what is the value of this ambiguity term. Well, this is, in general speaking, there is the lambda method that is a powerful method for ambiguity fixing that use the correlation between the different estimates, the different parameters. But this is the idea. Here we have a plot. I showed this plot before about the accuracy we can achieve. This is with real data, with single frequency, using only carrier, the accuracy we can achieve once the ambiguities are fixed in this navigation technique. Well, the key feature of RTK is the capability or the ability to fix the carrier phase ambiguities on the fly. That is while the rover is moving. There are some package, major receivers manufacturers offers solution package that consists on a pair of receivers, reference station and receiver, and the software to process the data. And the performance of RTK is measured considering the initialization time, that is the time we need for the first fix. These are typically seconds, and the correctness or reliability of the ambiguity fixing. That is the probability of how confident is the ambiguity fixing. And there is a trade-off between fixing the ambiguity quickly and getting the right value of the ambiguity. Typically, for baselines between 10 to 20 kilometers, we can fix the ambiguity and achieve this highest accuracy, centimeter level, in few tenths of seconds. It depends on the satellite geometry, but in 10, 20, 30 seconds, we can achieve this high accuracy. Well, the main problem of the RTK is this limitation in the baseline. That is the distance between reference station and receiver. And as I commented before, this limitation is due to the ionosphere, because for long baselines, we can not assume that the ionosphere is the same, the ionospheric error is the same at the reference station and user receiver. The residual error becomes large, and then the ambiguity fixing is not working properly. This means that if we have to cover a wide region or even a country, we will need large number of reference stations. For instance, we need about 30 stations to cover 10,000 square kilometers. This is like the Corsica Island or the Cyprus Island. Then, as I commented before, this limitation comes mainly from the atmospheric propagation error, mainly from the ionosphere. Then, how to overcome, how to improve, how to extend the baseline? Well, the idea, in order to extend the baseline, is to use a reference station network instead of using a single reference station, to use a reference station network, and using this network to compute an atmospheric propagation model in order to, in general speaking, to mitigate the atmospheric propagation error. This is the idea. The idea is to have a reference station network collecting data. This data is sent to a central processing facility that computes these atmospheric propagation errors. Okay, how it works? Here we have one of the examples of the real-time network is the virtual reference station. And the idea is we have a reference station network that collects measurements and compute this atmospheric propagation error on one hand, and on the other hand, this central processing facility using this atmospheric propagation model is able to emulate a virtual station close to the user. This means the operation way is the user goes to the operation region, the working area. When the user is in the working area, computes an approximate value of his coordinates, and these coordinates that can be computed using only code. It is not necessary to have a precise value for the coordinates, and then send his coordinates to the central processing facility. And the central processing facility, using the information of the reference station network, emulates a virtual station, like a real station, but virtual station, close to the user, where in the generation of this virtual station, the atmospheric propagation model has been taken account in order to generate the conditions close to the user. And then the user can proceed in the same manner as in a typical RTK survey. It's not necessary to upgrade any software. What he needs only a radio link in order to connect with the central processing facility, but this can be even a mobile. So, okay. The limitation of distance, let's say the baseline, using this technique can be extended to over 15, even 100 kilometers, which is not bad. It depends on the geographic location and the network and the level of the ionospheric activity. But still, if we have to cover a continent or a wide area, even having these large baselines, we need to deploy a wide reference station network. For instance, in this case, we need about from 5 to 10 reference stations to cover 10,000 square kilometers. This is Corsica or Cyprus Island, on one hand. On the other hand, this real-time network is limited by the data link coverage, system latencies. The availability depends on the network extent, depends on the extent of the region where we have the network deployed. Is affected by the network density, and in the case of this implementation, in the case of the virtual reference station, we need a two-way communication link. One way to send the user coordinates to the central processing facility, and another way to send the central processing facility the virtual measurements to the user. Next one is PPP, precise point positioning concept. In PPP, we will achieve the decimeter level accuracy, but there is no any limitation in the baseline. This is worldwide, but it takes longer to converge. Here in RTK, we can achieve in few seconds, high accuracy, but here we need half an hour, even 1 hour, depending on the satellite geometry. And this is the idea, this technique, PPP, precise or absolute point positioning, was proposed at the end of the last century, at the end of the 90s. And when it was proposed for post-process mode. Now it's working in real time, but at the beginning was a technique developed for post-processing, not for real time. Now it's working in real time. And the idea is, on one hand, we have to use precise orbits and clocks. We have to use, here we have to model everything as best as possible. The target is to achieve centimeter level of accuracy. And now we have not the measurements of the reference station. This is not like the previous case where we have the measurements of the reference station, and using these measurements, we take differences and we remove common errors. Here we use precise orbits and clocks. These precise orbits and clocks has been computed from a reference station network. Then, instead of reference station measurements, we have computed differential corrections. We have precise orbits and clocks. Then, because the target is to achieve centimeter level, we have to model everything as much as possible. We have to model everything at the centimeter level. Orbits and clocks are at the centimeter level, but we have to deal with all terms, error terms that Adrià has commented before. Let's say not only accurate orbits and clocks, but also we have to deal with other additional terms like the antenna phase center, because these involve centimeters and the target is to get centimeter level of accuracy. Even with the solid tides, what does it mean, solid tides? Solid tides means that the solid surface of the airs is moved due to the sun and moon attraction, like the water, like the oceans. And this can vary by up to 20 centimeters. And then if we want to achieve absolute positioning with centimeter level, we have to account with this up to 20 centimeters. Then we have to model everything as much as possible. In the case of RTK, in the previous case, there is no problem with solid tides because reference station and user are close and in local area, and then they move due to the solid tides in the same way and cancel in differential mode. The error component more difficult to remove is the ionosphere. Well, in PPP, we need dual frequency receivers in order to remove the ionosphere. The idea is as follows. The ionospheric error depends on the frequency, depends on the squared inverse frequency. This means that using signals at two different frequencies and using this combination of signals, L1 and L2, we can remove the ionosphere, the ionospheric error, at the level of 99.9%. Then, in this way, we remove the more difficult component of the error to deal. Okay. As I commented before, the PPP, precise point position, it was developed at the beginning for post-processing mode. This means not for real time, but now this technique is working in real time. This means that some centers or even some service provider for commercial application are computing orbits and clocks in real time, and these orbits and clocks are provided to the user to perform PPP in real time. Here we have a web. Here we have an example of these products. This is here we have a plot illustrating the performance. These orbits and clocks are broadcast in the RTCM format using what is named state space representation, where these components of the error are split independently. The pros and cons of PPP. Well, the good news is that PPP, precise point positioning, provides absolute worldwide positioning for a single receiver. We have not to buy two receivers in order to perform differential positioning. We need only a single receiver and a service provider, of course, for the orbits and clock. On the other hand, the state space modeling is the idea, the splitting the differential corrections in orbits and clocks is more close to the physical error of the sources. And this allows to reduce the message bandwidth because we can consider different time updates for these parameters. The main problem is the large convergence time. As I commented before, the decimeter level navigation needs tens of minutes, even 1 hour, depending on the satellite geometry. And also, the accuracy is not as good as in the case of RTK, because, well, it depends the time span. In this case, in PPP, the ambiguities, we cannot take benefit in the classical PPP. We cannot take benefit of using the information about the integer nature of the ambiguities as we do in the case of RTK. Because the ambiguity parameter we are estimating here is a combination of the integer ambiguities plus the receiver and satellite hardware bias plus these real valued terms. Here we are not using double differences of ambiguities. Then the ambiguities are real valued term. And we estimate these ambiguities as real number. This is what we call to float the ambiguities. And then there is some estimation error, some not only the conversion time, but some estimation error. But the idea is if we take a long observation time, long observation span, the filter converges and the solution will be close to the solution we get in RTK, quite close. But the problem is that we have to take longer and longer. RTK provides the high accuracy in seconds, in few seconds, as I commented before, but the problem of RTK is that if we want to fix the ambiguity quickly, there is some probability of having a wrong fix. Then, and when we have a wrong ambiguity fixing, the position is degraded. But there are techniques in order to assure that the ambiguity fixing is fine in order to reduce this probability of wrong fix. Well, here I'm going to present a brief summary about we have presented before about differential GNSS with code, RTK, and PPP. This is just a summary of this lecture. This is the part that my colleague Adrià has presented before. This is standalone positioning, code-based positioning. The idea in code-based positioning and everywhere is that everywhere in differential positioning is that errors are similar for users separated tens, even hundreds of kilometers, and these are removed or mitigated in differential mode, improving positioning. In using the standard positioning, the standalone positioning, that is the positioning that we can achieve using our mobile, we get accuracy at the level of few meters, but worldwide. There is no restriction in the baseline in single epoch. Each epoch, we can compute an independent solution. Even we have single epoch in the code-based differential positioning, but here we improve the accuracy. Meter level of sub-meter level can be achieved, but there is a limitation in the baseline. Here, using code, we can extend the baseline up to 100 kilometers. The idea is that we can accept residual errors larger than when we work with carrier phase, because here the error of code is meter level, and we can assume residual errors at the level, meter level, or decimeters level. This is not as strict as with carrier phase positioning. And here there are the main concepts. In the standalone positioning, we use a single receiver, single frequency, and we use broadcast orbits and clocks. Let's say we use the orbits and clocks broadcast by the satellite. We don't need any additional service provided. We don't need any additional reference station. The modeling must be at the meter level. We use code measurements or carrier smoothed code in order to remove, to smooth the code, to reduce the noise, the code noise. No ambiguity fixing is needed because we are using code. In the case of differential positioning, as I commented, the idea is that their errors cancel in differential mode. We use single receiver, one frequency, plus compute differential correction, plus the pseudorange corrections computed by the reference station. And the errors are removed from using these pseudorange corrections, using these differential corrections. There is a degradation with the baseline, as it has been shown by my colleague in the experiment, and we use smoothed code. Code measurements smooth with carrier. As I commented, we can achieve meter of sub-meter level in a regional area and in single epoch. Carrier-based positioning. Well, we have relative positioning and precise point positioning. These are the accuracies. Now, neither works in single epoch. We need seconds, but few seconds in order to achieve this high accuracy. In RTK, we need minutes, tens of minutes, even the best part of 1 hour in PPP. This is not the case when using code, where we can achieve the positioning in single epoch. We can get one solution at each independent epoch without widening. There is a limitation in RTK to few kilometers. This is mainly due to the ionosphere. The residual ionosphere, when taking differences between reference station and user, must be few at the centimeter level of less. This make a limitation in the baseline. But in PPP, there is no limitation. This is worldwide. And here there are the main ideas. Well, I has commented before this. In the case of code-based, there is no limitation, there is no ambiguity involved. In RTK, we use double differences between pairs of satellites and receiver, and we use double differences in order to remove the real valued terms that corresponds to the satellite and the receiver. Remember that among the integer term, we have two real valued terms, One of them corresponds to the satellite and the other to the receiver. And in double differences, we remove these real valued terms, and then in double differences, the ambiguities are integer numbers of wavelengths. And we can use this information in order to fix the ambiguities. On the other hand, because we are taking differences, is the same taking single or double differences, the errors are removed or mitigated due to this taking differences of measurements. Well, there is a limitation of baseline, but we can achieve this centimeter level in few seconds. In PPP, we use a single receiver. This is absolute positioning, but we need dual frequency measurements. We need two frequencies in order to remove the ionosphere, because the ionosphere is as I commented, is the component of the error most difficult to remove, to model. Then, and using dual frequency receiver, we can remove the ionosphere at the level of 99.9%. And we need a service provider for the orbits and clock. Precise orbits and clocks are computed from a network or reference station, and a service provider has to broadcast this orbits and clock in order to precise model the measurements. It is necessary and accurate measuring and modeling up to the centimeter level. This was not the case when using double differences, when using RTK, because most of the error cancels in these double differences. Here we need to model everything. One example is, as I commented before, are the solid tides, or the antenna phase center, or other term is the wind up in the carrier. In this case, carriers are not fixed, are floated. This means are treated as real number. We cannot take benefit of having the information of using integer numbers. This is because the ambiguity term we use here is a real valued. It contains the real valued terms due to the hardware bias of satellite and receiver. Well, then because we are floating the ambiguities, we have to decorrelate these real valued ambiguities from the coordinates and also from other parameters like troposphere. Troposphere is estimated in the filter, and it takes longer. It takes longer to converge. This is the best part of 1 hour. Okay, and here is here ends the presentation of carrier-based differential positioning, and just very quickly some ideas about commercial services. I will be quick because it's a bit late. Here we have two examples. The idea is to tell that, well, there are service providers that are computing these differential corrections for commercial users. There are several service providers. Here we have an example, Trimble as an example, Trimble and Fugro. Trimble is more devoted to agriculture, and Fugro is devoted to operations at the sea. And they have similar products. In Trimble, we have OmniStar, and we have 4 different types of products: virtual base station, worldwide service, XP, high performance service, OmniStar, and similar products are provided by Fugro. Well, these products are, for instance, the OmniStar. This provides sub-meter level of accuracy using a single frequency. This corresponds to the code-based differential positioning that has been presented by my colleague Adria. This is code-based differential positioning. Using a smoothed code, we can achieve sub-meter level accuracies. The second one is OmniStar XP. This is worldwide, and it needs dual frequency. And as you can imagine, this corresponds to PPP, precise point positioning, where we have orbit. We need orbit and precise orbits and clock corrections in order to perform this PPP, precise point positioning, and the accuracy is at the level of decimeter level. And finally, we have the OmniStar, where this is the most accurate solution, where the accuracy is better even than 10 centimeters. This is the virtual base station. This is the highest accurate solution, virtual base station. And in this, using this network or reference station in a region, they provide they emulate the virtual reference station close to the user, and the user can navigate using this data at centimeter level. The accuracy is better than 10 centimeters. And finally, there is another product. This is the worldwide dual frequency. This is PPP, but in this case, this is for not only for GPs, but also for GLONASS. This is an example. They are offering new products, and now they are offering even they are going to offer multi-constellation, let's say GPS, GLONASS, Galileo. Well, the idea of using more than one constellation is important in order to increase the number of satellites available. And this is useful for urban cannon, where we have the buildings masking the satellites. And also, this is important when in some areas under scintillation. Scintillation are rapid fluctuations of the signals that can produce frequent cycle sleeps, even loss of the signal. And then if we have more satellites to choose, we can improve the navigation. Well, and that's all. In our web, you have more material. You have slides, and we have also a book. This is for free. You can download the PDF of this book on GNSS data processing. This is for the theory, and this is for the laboratory exercises. Well, that's all. Thank you very much for your attention.
Okay, thank you very much, Felix, Adrià, Jaume. I think we have time for a few questions. So we have a question from Professor João Francisco Galera Monico. The question is, let me see. Just a minute. How to get the uncertainty of the time delay? Is there correlation between different satellites or channels?
Maybe this is referring to my part. I can try to answer the first question. So the uncertainty of the time delay estimate, we can calculate for the maximum likelihood estimator that I have shown. We can calculate something that's called the Cramer-Rao lower bound, which is a lower bound of the estimation error for an unbiased estimator, and the maximum likelihood estimator asymptotically achieves that bound. We have seen that the delay log loop is an approximation of a maximum likelihood estimator, so it is not exactly a maximum likelihood estimator. We can calculate for all different kinds of delay log loops, looking at the closed loop transfer function of the loop. We can calculate a time delay estimation error with respect, for example, to the power of the received signal. The second part of the question is, yes, there is correlation between the satellites. This is called multiple axis interference. There's even correlation or interference between the different systems that share the same band. So the the system Galileo is interfering the system GPS to some extent, and vice versa. The system GPS is interfering the system Galileo in L1, for example. With the respect to the question, there was also mentioned the number of, or the word channels. Maybe the question is targeting if the observables in the receiver, which are coming from one of the receiver channels, if they are correlated. In my opinion, yes, they are correlated because of the multiple axis interference. If, as I showed on one of my slides, if we correlate with one code, the incoming signal. So we have a high correlation with the desired satellite, but we have also correlation with all the other satellites. And this depends on also the Doppler of all these satellites, the time delay, the phase, and so on. So this is also changing over time and is dependent on geometry and signal parameters.
Okay, thank you, Felix. Another question from Ramon Morales. Any news about how to mitigate the scintillation effect?
The question is, well, scintillation is difficult to mitigate. I can talk at the level of the navigation, not at the signal processing. I can talk about the level of mitigation. Scintillation depends on the region. In high latitude, scintillation is different than in low latitude. The worst scenario for scintillation is in low latitude. For instance, in Brazil is here scintillation produce not only cycle sleep, but even strong, even loss of signal, phase, and so on. In high latitude, scintillation is refractive. Refractive means that can be the effect of the ionosphere, and scintillation can be removed using the combination of two signals. Then the only problem we have there is that in high latitude, having scintillation, we can have more cycle sleeps, but this is not too critical. Even we have a paper where we show that we can navigate, we can make PPP under scintillation conditions in high latitude. The problem in low latitude, the situation is worse, because in low latitude, scintillation is not only refractive, is diffractive. There is diffraction. And then this diffractive behavior cannot be removed using this combination of signals. And the situation is worse. Yeah, this is from the navigation point of view, not from the signal processing.
Okay. Yeah, maybe I can comment on the signal processing part. There are several methods in the literature already available that use Kalman filters to track the signal. And these Kalman filters, they use not only a model for the propagation of parameters of the direct signal, so from the satellite, but they also use models that model the scintillation effects. There are even already some papers out. One of my students, or former colleagues of the German Aerospace Center, she has developed a method which is estimating the model of amplitude and phase scintillations online inside the Kalman filter. And I have another student is working with from INPI, where I'm collaborating with INPI a lot, and we have been looking also into Kalman filter structures and traditional loops, also how to tune traditional loops like a DLL, a PLL, FLL loop to be more robust to scintillations. And there's always the question, this is my last comment, is there's always the question if we want to monitor or if we want to be robust. So if we want to monitor scintillations, we want to estimate precisely the phase and the amplitude in order to learn about these effects. And on the other hand, we want to be robust. So the receiver can be tuned. Even standard receivers can be well tuned to have a very high resilience to scintillation effects. Then the receiver is not following precisely the phase estimates, but he's like averaging over a longer time or is smoothing for a longer time. However, there are severe cases here, especially here in Brazil, where we have large drop of the power of the signal up to 15, 20 dB for several seconds. And then this is getting very difficult to track this. If these fades are not too long, then the receiver can survive. But if the fade is too long, then you can switch to a multi-antenna system on the receiver side and try to enlarge your array gain, antenna gain using several or a group of antennas. And this is also a method that I've been working on in my past. So there is a lot of so to close this, there's a lot of publications on this, and I have recently seen this is a topic gaining more interest again. If you look at the sessions of the ION conferences and also at some IEEE conferences, and certainly for Brazil, this is, I think, one of the most important topics to be solved on the signal processing side to make robust and reliable positioning possible even in these conditions.
Okay, thank you very much. Well, you talked about RTK, but Miguel Espinosa has a question about what is your opinion about RTX from Trimble?
I don't know this one. I cannot give any opinion. I assume that RTX should be a commercial package of software. I don't know.
Okay. And about RTK accuracy, Miguel Espinosa asks you how L5 improved the RTK accuracy.
My opinion is that the accuracy would be at the same level. I do not expect to have better accuracy, because among the carrier we have as I commented before, the errors not fully cancelled. There is some residual error, and it depends on the baseline. But in my opinion, will be mostly the same.
Okay. Another question from Carlos Fuentes. The question is related with this hardware used to implement the algorithms. Which technical considerations related with the certification on the embedded system used to develop the receiver? I think it's not very clear, this question. Maybe if Carlos could send us the question again, it would be better. Rubens Ferreira Jr. If we use multiple antennas, could we reduce the conversion time to PPP?
No, because the conversion time, the convergence time of PPP mainly depends on the quality of code. If using multiple antennas you can reduce the noise, the wrong noise in the code, it will help. This is the idea, because the convergence time depends on the error, on the quality of code measurements, on the noise. This is at the beginning. Then, if the target is to reduce this noise, yes, it will help.
Okay, thank you, Wellington Jr. And Luis Roberto. They sent us the link, the web link about RTX technology is the PPP solution from Trimble. It's already in the chat.
Maybe I don't know, but maybe because the evolution of PPP's evolution is evolving in two ways. PPP with ambiguity fixing on one hand, and other hand is fast PPP. Fast PPP is the use of the ionospheric information data in order to speed up the navigation, filter. Maybe the solution that he refers is about fixing ambiguities in PPP. Well, the idea is, as I commented before, the problem of PPP is that in classical PPP is that the parameter that we are fixing is a real valued parameter. The ambiguity we are fixing is a real valued parameter because it contains the hardware bias of satellite and receiver. Then, one way to overcome this problem is, at the same time, the central processing facility compute orbits and clocks using the information from a network or reference receiver. At the same time that compute orbits and clocks, the central processing facility can compute carrier hardware bias for the satellites. If this carrier hardware bias, these real valued parameters, are sent to the user can remove this real valued part of the ambiguity. It remains the hardware bias for the receiver, but this is not a problem because taking differences between two satellites can be removed. Then in this way, in this PPP, using this additional information, this carrier hardware bias for the satellites, in this way, it is possible to remove the real valued parts and have an integer ambiguity to fix. Yeah, this helps to reduce the convergence time because when the ambiguity is fixed, the accuracy improves quickly. But this is not a solution from Trimble. Many people are working in this. We have some papers in this also. This is one solution. Another solution that can be applied together with the solution with ambiguity fixing is the fast PPP. Fast PPP, the idea is to use, as I commented before, ionospheric information, very accurate ionospheric information data as an additional information in the filter in order to accelerate the filter convergence, in order to reduce the convergence time. The ionosphere helps, provided that the accuracy of this ionospheric information is better than the code. Because at the beginning, the convergence is driven by the code noise. And if you provide external information with better quality than the code, like this ionosphere, it will help. This is the fast PPP technique that we patented in 2000 something, 10 years ago. But there are several groups working also in this, using ionosphere to accelerate. And the best goal is to have PPP with ambiguity fixing. There is nothing else with PPP. You cannot do nothing else. For sure, the solution from Trimble applies one of these techniques or both, but no more, because there is no more.
Okay, thank you. Felix, a question from Daniel Araújo. Are there research lines to investigate other pulse shapes that can provide enhanced resolution in the synchronization task?
Yes, there's a group of research or an expert group supporting the Galileo program in Europe. I have been part of this group for several years, and there's I guess, more than 20 institutions in Europe that work on signal design for Galileo and to enhance the performance of the signals. Especially right now, they're working on evolution of Galileo, where they plan, what I've understood, also to enhance some of the signals. In the US, it's the same. There are groups around MITRE, the Aerospace Corporation, and others that are working on optimizing signals and deriving new designs. And I myself worked at this also in my thesis, for example. So yes, clear yes.
Okay, thanks. Another question from Carlos Fuentes. Is there any differences between the algorithms developed for different applications? For example, aeronautical, civil, and military applications?
Yes, of course. For instance, for avionics. In avionics, the target is not the accuracy, it's the integrity. And integrity means that the user must trust in the quality of the corrections. And the metrics is for instance, this is for avionics, this is in weight area, in WAS, Weight Area Augmentation System, or EGNOS in Europe. Then it is necessary to assure that the probability of error, of having an error in the signal, is less than 10^-7 or something like. And also continuity, availability. There is a very stringent metrics in avionics. This is not the same, for instance, for agriculture. In agriculture, if you have an integrity failure, there is no problem. Yeah, of course, there are different algorithms. Yes, yes. It depends on the application. And even for application it depends, because even the concept of integrity is different for avionics, for maritime, for other application. Yeah.
Okay, one last question from Daniel Araújo. How do you see the use of machine learning techniques to provide more precise models to assist in PPP or RTK, for example?
We are not using this. I cannot answer. Sorry, I cannot answer this question. For sure, there are people doing good research on that, but I have no idea. I'm sorry.
Okay, we have few questions that we can answer before the webinar by email. And before we finish the webinar, actually we're going to answer the questions after the webinar by email. And before we finish the webinar, I would like to ask the speakers your final considerations and what recommendations do you have for anyone who wants to find out more about GNSS, EGNOS, Galileo. Where can they find further information about this topic?
Okay, well, let me answer that. I would recommend everyone interested in learning more about GNSS and the activities in the particular field of Brazil to check the website of the Galileo Information Center. That would be the first stop. In this regard, we plan to organize a summer school for next year that will be organized in Fortaleza. It was due to happen this summer, but because of the COVID situation, it was decided to be postponed to next year. So I would really encourage anyone willing to have this summer school, to attend this summer school, to get an insight on the signals, on the processing, but also on the navigation. It will be like some 10 days of summer school, and we will provide a lot of background and laboratory exercise, and we would really recommend anyone to attend this school.
Okay, and also in the Galileo Information Center Brazil website, it's in the chat now. You can find further information about GNSS, EGNOS, and Galileo. Well, thank you very much for your attendance. The feedback in the chat was very positive. I also would like to thank the speakers for your time to the test sessions and preparing and presenting the lectures. And I invite all our audience to visit Galileo Information Center website, which is already in the chat. And just to remember, Galileo Information Center in Brazil has the objective of dissemination and promotion of Galileo satellite information and to promote new applications in the region. And just my final remarks, the webinar replay will be available soon in the Galileo Information Center website, as well as the slides in PDF format. Lots of people were asking in the chat about the slides, so I confirm that the speakers allowed us to put the slides in the website. Okay, thank you very much. Take care. Use masks, and see you soon. Bye.
Bye-bye. Thank you very much.
Bye.
Thank you.
Goodbye.